Okay.
There we go.
Stop. Okay, it's recording. I'm not going to touch a thing. All right, so we are recording, and I'm very happy to have Dr. Julie A. Adams here today to give us our final tech talk. We saved the very best for last. And she's a professor of CS and associate director of research for CoRIS. That's a collaborative robotics and intelligent systems institute here that some of you may know about. There's a webpage if you don't know about that. But she came here from Vanderbilt University a few years ago. We're very lucky to have recruited her from there, and she's there she had the human machine teaming lab, and basically has started the same type of lab here, expanding her work a bit. She's done a lot of work in human machine teaming, over 25 years of work, so she's really renowned in that area, and has been doing more and more with aerial vehicles. So she's done a lot with manned and unmanned vehicles, and has lots of UAVs flying around these days, working with those challenges, and has been involved in policy as well. So a lot of experience there. She's part of the FAA's Ashore program, which is one of the main, it's going to be a very important program to sort of decide how UAVs are going to be integrated into the airspace in the years to come. And they will be. So without further ado, I'd like to let Julie take the stage. And basically for questions, I don't know, Julie, do you like people to unmute and interrupt, or just put them in chat? Do you have a preference?
What I'll do, Alan, is I've got different segments in the talk, and I'll probably just stop and ask if there's any questions. I'll try to remember to do that. Okay.
All right. And if not, we have time at the end as well. And so save up your questions for that. All right. So go ahead, Julie.
Okay. Great. Thank you. So thank you, Alan. Actually, the name of my lab here at Oregon State is the same as it was at Vanderbilt. It's the Human Machine Teaming Laboratory. And I like to say that I have a tertiary research personality. So while my degrees are computer science and I do distributed artificial intelligence research quite a bit, my PhD was really in robotics before a PhD in that area existed. And then also because of my dissertation research, I focus on human factors and the human interaction aspects. So I actually also have courtesy appointments in mechanical engineering and industrial engineering here at OSU because of those aspects of my research. So my research group is pretty large, and we cover a vast area of topics. I've worked in robotics since 1990, primarily with ground robots until the early 2000s, when I started working also with aerial robots. We did some of the first deployments for mapping of structures in the Andes Mountains. And then since I came to OSU a few years ago, I've started working also in marine robotics. So what I want to talk about today is, robots are becoming more prevalent in our everyday lives, autonomous cars, various things like that. And there's a lot of conversation about, well, how do we trust these robots? How do we get the robots to explain what they're doing and thinking? And there's really a lot of focus on those two kinds of topics. And my argument is that those aren't enough. You really have to have this broader concept, which is called transparency. And so what we're going to talk about today is, what is transparency and why does it matter? We will, if I can get my screen to advance. There we go. Hopefully it is now where it needs to be. So these are some examples of real world robots, some of the things that we work on here at Oregon State. So you see Digit from Agility Robotics, Jonathan Hurst startup company in Albany. There is work out of civil engineering and using drones for inspecting bridges and other infrastructure systems. Bill Smart has worked on using robots for Ebola treatment, the picture in the upper right here. And of course, autonomous cars, and then underwater or surface vehicles that Jeff Hollinger and I and others are working on. These are all examples of systems that are going to necessarily have some interaction with humans. They're more, if you will, utilitarian in their use. So Digit, for example, is delivering packages. We're not necessarily expecting it to have a happy conversation with the person that they're delivering the packages to. However, it should not be intimidating as it's walking down the street in this picture with the woman and her daughter, for example. Same thing with autonomous cars. They shouldn't be intimidating. And, you know, we should be able to understand from those autonomous cars what's happening, just like we would from a driver of a vehicle today. So some of that is an essence of trust. Some of it is also an essence of the system being able to be clear on what it is capable of doing, what it's possibly going to do in the next few seconds, etc. Now, when we start talking about these last two images that just came up, so the sub-T challenge here, which is ground robots, and there's also aerial robots in these underground environments that Jeff Hollinger is working on with Carnegie Mellon, then the transparency is very different here because you have long periods of time without communication with the vehicles, and there's coordination that has to come into play. There's multiple vehicles, and it makes it more complicated. In the jellyfish robots down here on the bottom, this is Heather Knight's work, where really are kind of looking for that social interaction. It's much more about, this is actually a dance being performed by two dancers with the jellyfish robots, and it's supposed to give an overall expression of the dance. And so there it's a very different perspective. You've got multiple robots, but you don't really necessarily have to trust them if you're in the audience. You just have to be able to understand what the intent is out of the performance itself. So there's a lot of different ways that we would look at these systems and how we would express, they would express what's going on with them and why they're in a current state or they're doing what they're supposed to be doing, etc. Now, there are some areas in which there is more regulation. So for example, Alan mentioned the FAA and drones. So there is definitely aspects of regulations that are being investigated and being developed by the FAA for the integration of drones into the national airspace. Sorry, my air conditioner is making a weird noise. Hopefully you can't hear that. And you know, one of the projects we're working on is how do we have multiple drones in the airspace, such as delivery drones. Same thing with vehicles. There's a lot of regulations that already exist around cars and trucks, but we have to have additional regulations that impact autonomous vehicles, and that will also have some development of expectations for people such as those walking across the street or even people riding in the vehicle or remote supervisors of those vehicles. So I work specifically, one of the projects I work on, and I have a lot, on the DARPA Offset program. And I am co-PI with Raytheon BBN on one of the integrator teams. And we work on this project along with our collaborators from Smart Information Flow Systems. The purpose of this project, and we're now in our final year of this project, is to be able to deploy 250 vehicles in an 8 to 10 city block area for doing a mission that has multiple phases. So going out and collecting information and identifying what's happening in the urban area, trying to identify where we need to do more work, and then actually going out and doing that work, whatever that work may be. Our missions can last up to 4 to 6 hours. And in our prior missions, we've flown 2 different types of UAS. So both of them quadcopters. The picture here in the middle is a 3DR Solo. So if you're familiar with those vehicles, you know they are quite old. They don't have the really sensors beyond a GPS and an IMU and a barometer. So we have outfitted them with Pi cams and Raspberry Pis in order for them to be able to do something useful in the environment. This is an UVIF EFO, which has more sensor and processing capability. And then our ground robots, we have 2 types of ground robots, both of them ion robots. This is the R1 that's pictured. We also have the R6, which has 6 wheels. So, you know, in this context, you know, we have to have very cheap vehicles. And we are functioning in environments where we cannot rely on cellular or Wi-Fi to provide communications to our vehicles. And we have to assume that we are going to have dropouts in communication with our vehicles. We also have to assume that the vehicles are going to have GPS error. So there's a lot of time where we're getting either inaccurate or unreliable information, or we're getting no information from the vehicles. And so that makes this aspect of explainability a bit harder. And it makes trust have to be much higher that the vehicles are going to go off and do what they're supposed to do. But you also have these other aspects that really come into play with transparency and understanding what's going on in the system. For our final deployment later this year, we're integrating 2 fixed-wing UAS, a smaller one that will provide persistent surveillance over our operational area, and then another larger fixed wing that will actually do information collection about buildings. And we're also integrating yet another quadcopter because we need to be able to go from outdoor areas that are GPS available to GPS denied areas inside of buildings and be able to fly around buildings and collect information. In our case, we use an LTE base station, but even then we can't cover our entire area and you have blind spots because it's line of sight communication. So these are all aspects that we really need to be thinking about when we want to put these robots out into the real world. So what I want to do next, and then I'll pause for a moment, is tell you what I mean by transparency. So the concept of transparency was developed by Jessie Chen and her colleagues at the Army Research Laboratory for a single human robot system. And the idea here is that the system is able to allow the human to understand what it can actually do. So what are its affordances? And then also to help the operator understand what the robot is going to do, why it's going to do it, what's happening in the environment. And then in addition to that, also being able to communicate its performance, its plans, and its reasoning processes. Now, this sounds like a lot of information. And the analogy that I would use here is you have to balance that information and what's important. If you have a 2-year-old, whether it's your child or grandchild or niece or nephew, you know, you have to communicate with that 2-year-old very differently than you do an adult. You can say to an adult, go over there and point, and they completely understand. Whereas a 2-year-old is probably not going to understand. And as you give them more complex, high level direction, the 2-year-old's going to fumble. You have to provide them with more detail. That's basically where robots are today, even with reasonable levels of autonomy. Either the autonomy has to give them the direction or the human does. And in some systems, it's really still the human doing a lot of the direction. So we want to be able to move away from that, develop the autonomy, and have this ability to communicate this information. So as part of their work, they developed this framework called the Situation Awareness Agent Transparency. And you might have heard this term situation awareness before. It gets used a lot and often incorrectly. And what it really means, in the proper usage, what it really means is a human factors term intended to capture whether or not the human has perceived what's going on in the environment, is able to process that information, understand what it means, and then is able to use that information to project into the near future what is going to happen. So even if you're assessing perception and the human's ability that they've perceived something, it doesn't necessarily mean that they have situation awareness. They can also have situation awareness even though they don't necessarily perceive some nuance of the environment that others may believe is necessary for situation awareness. That has to do with the individual's differences in their training, just the way that they perceive things, a lot of psychological, physiological aspects that impact those aspects of human awareness, if you will. This transparency framework leverages that concept of situation awareness, but it also leverages a calibration model for trust, which is the 3 Ps mean perceptions, plans, and, oh, shoot, I just forgot the other one, processing, I think. And then there's an AI-based framework, which is beliefs, desires, and intentions. And this is not surprising given Jessie's background. I mean, Jessie is more of a computer scientist, human factors type of person like myself. And so trying to bring together some of the AI aspects and the human factors aspects. Within this framework, there's 3 levels. And this is really focused on the agent, and the agent here being robots. So level 1 is kind of that first level of the agent knowing what its status is, what it's perceiving, what its actions are, and what its immediate plan is. What is it doing right now so that it can communicate that information to the human and the human can have that basic level of understanding about what the agent has going on right now. The second level is the agent having the ability to communicate how it's reasoning. So this is more towards explainable AI in some regards, but it also has to be able to explain potential constraints or affordances about the environment that is impacting how it's reasoning about things. Is it using a particular vision processing algorithm over another because of, say, lighting differences in the environment? When you talk about underwater robots, it might be that it's using, it's on the surface, so it's using satellite communications, but now it's underwater and it has to use an acoustic modem, for example, things of that nature. And those two differences make big differences in what can be communicated to the human and how quickly the human gets that information. Level 3 is the agent's projections about how is what's happening in the environment going to impact its ability to achieve whatever its goal is, and perhaps the intermediate goals. What are the things that it doesn't know about that potentially it needs to gather more information about? And then how likely is it to achieve its success? So if the robot is planning a path, almost never, unless you're an autonomous vehicle where you're on a road, which is a more constrained environment than the types of places that I work in, in the types of places I work, almost never do your plans actually go the way you expect them to. So, how is it able to communicate that information to the human? Now, transparency, if you want to think about what it is in more general terms, is this principle of how do you provide information that is easy to use for the human and can be exchanged between the human and the robots to promote the human's understanding of the shared awareness, intents, roles, interactions, performance, future plans, and reasoning processes. If you've ever played a team sport, then you have a little bit of understanding what I'm talking about. You want to think about your robot partners like you would your teammates on your soccer or basketball team. That there's all these different nuances in the way you communicate or you perceive what's going on is very similar here. So the next slide is an eye chart. I don't expect you to understand it. What you should take away from this slide, though, here's transparency in the middle. And then these ovals are what we call direct factors. These are factors that directly impact a system's ability to provide transparency to the human. And then the gold rectangles are what we call indirect factors. And there's a number of different things here. So you do see explainability here, you do see trust, but you see other factors. Some of them are more usability oriented, such as human-computer interaction, but some of them are more physiological, for example, like performance or understanding. And then you do see common human factors aspects, such as workload and situation awareness, and then other aspects that really have to be built into the system. And while I'm showing you this in 2D, sorry, it's actually 3D, and there's multiple different connections between these nodes. So this concept of transparency for human-machine teaming is really important if we want to build robots that are going to be used by different users in different contexts. So I think, yeah, so I want to transition to talking about 3 different types of robots, but if there are any questions about what I mean by transparency at this point, what I'm going to do going forward, we're going to talk about 3 different robot contexts, and we're going to talk about some of these transparency factors for different users. Alan, I can't see the chat, so. Where's the chat?
Nothing in chat yet. So I think okay. You can just move on.
Hearing nothing, I continue. All right. Sorry, things are in the way here. There we go. All right. So we're going to go back to Digit. And I said before, Digit is a robot. One of the purposes of the company has been working with delivery companies to deliver that last mile from, or not last mile, sorry, from the sidewalk to the door, that last portion of the delivery from the truck to the person. And Digit is able to do that, is able to go up and down stairs. So in the context of COVID, although when I created this slide, we were in the height of COVID, You might think about using this robot for community contract tracing and testing. So we want to think then about who our different users are going to be. You're going to have the home resident. That's going to be one user, and it's pretty diverse when you think about that. You've got adults, you've got children. You don't know who's going to actually answer that door. You also have lots of different languages you have to be able to accommodate. English is not always the language that's used in every household. You also have to think about disabilities, be it visual, cognitive, or physical, that can impact the human's understanding of the robot, provide different perspectives. You know, your perspective standing up, answering the door, looking at this robot is going to be very different than if you're, say, in a wheelchair, or if you are, you know, an 8-year-old looking up at the robot. It could be a bit frightening. And then there's also this whole question of trust in the government, right? If this robot is coming out, what else is this robot collecting about you? Is it collecting information about your home while you have the door open? Is it taking pictures of you? Is it collecting, you know, what information is it collecting from you, and how secure is it? From the other side of this, if you're talking about the local or state, county government that is attempting to collect this information, there's a different set of factors that you need to consider. Is it collecting the data accurately? And is it in compliance with any of the constraints that may be on it, regulations or instructions, et cetera? You know, there are HIPAA requirements, for example, that may have to be considered. Is it covering an area in a quick enough manner? The only way this robot's going to be useful is if it can do it as fast or faster than a human would, and less costly. And then, you know, what is the one-to-many data collection for the robots? So how many robots do you need? How do you collect information from multiple household members? Those kinds of things. And so you've got two different types of users with two very different perspectives. One of the things that we can assume about this context, or I'm going to assume, is that we are in an area where we have good cellular coverage. So the robot can be connected to a cellular link in order to be able to provide that information and adapt appropriately. And if we're in a more rural area, then we can assume that there is something like the Amazon truck, or you know, a Mercedes Sprinter van, for example, that the robots are coming out of, and there's communication from that Sprinter van to the robots in order for that information to be collected. So what does this mean in terms of the transparency map? Well, you can see that this map is much smaller than the one I showed you before that had all the factors. And I've got 3 that I highlighted in red because I think they're really important from the perspective of the civilian in this context. So this map is specific to that civilian resident needing to interact with that robot. So there needs to be a level of credibility. And while that relates to usability, it also relates to trust. But that credibility of the system, you know, how do you know it's not a scammer robot just coming to collect your information? You know, many years ago, for those that are older in the audience, you know, we wouldn't have thought about getting spam calls on our phones. Now we get them all the time, right? So while that may not be an issue yet with robots because there's still a novelty, that is something that, you know, people might be wondering about. Just like when a human comes to your door and is providing information for different types of context. You've got adaptability, which is really important in the civilian situation, because a robot not only has to be able to adapt to be able to get up to the door. Think about ringing somebody's doorbell. How long do you wait before they don't answer and you decide to move on? How many times do you press the button, right? That's just one aspect of adaptability, but then somebody answers the door, and think about all the different contexts that you have with the language, the size of the individual, if it's a child versus an adult, potential disabilities, etc. You know, how do you get them to keep the door open and interact with the robot and not just close the door and go away because it's a robot and not a human, right? They may feel less engaged with the robot, for example. And then there's context, right? So that adaptability requires that the robot is taking all the information from the current context in order to develop that trust, in order to impact the performance of getting the civilian to provide the information in a way that the civilian can understand, explaining things in a way that the civilian can understand, and then providing information in a way that the robot can understand from the human. So in this context, we are likely either talking about Digit using voice to interact with a civilian, or using something like a touchpad, tablet, or something of that nature, which would be the most accessible to the broadest set of the population. Then there's the government supervisor that's sitting back and kind of monitoring all these robots as they go through the neighborhoods, right? So you can see I've highlighted adaptability again, and I've highlighted credibility, but I've also highlighted history and context. So adaptability is similar here, but the adaptability to the government supervisor is more about making sure that the adaptability is resulting in accurate, reliable information being gathered. And, ensuring that that robot is doing the correct adaptations for the individuals that it's interacting with. The credibility here is a little bit different from the perspective of the government supervisor. Credibility means that the information being gathered is accurate with regard to the contract tracing, or the test has been conducted appropriately to actually detect the existence of COVID if the individual is infected. There's also an important aspect of history here. So if the robot is going back to the same area again, then from the government supervisor perspective, they may need to know, well, which houses did we go to the other day and which houses didn't answer, so that they can go back to the appropriate homes to gather information, or perhaps they go at a different time of day after people have come back from work, etc. So that history aspect is important for developing trust with the government supervisor. And then there's the context again. So the context not necessarily being how many times have you rung the doorbell, but what is the context with the individuals you're interacting with? And then also the broader context, is there someone coming up and trying to kick the robot as it walks down the street, things of that nature. So there's aspects here of the way the system has to understand what's going on that is different for this government supervisor versus the person in the home. So before I go on, I'm going to stop here because we're going to go to a completely different scenario. And I can't really talk about all the things in this, but the idea is to help you understand a few of the things that are important with the robots. Okay, hearing nothing, I will continue. So next I want to talk about a deployment that Jeff Hollinger and I did with the College of Ocean Engineering 2 summers ago in the Gulf of Mexico. So we were working with 3 oceanographers, but this is just one of them. And then this is one of the roboticists. And we were deploying 4 Slocum gliders. So that's this tube-like vehicle here. Basically, they go in the water, they use buoyancy to sink down, and they stay underwater. In this mission, they were staying underwater for 3 hours. They can stay under for longer. What they use is they use buoyancy to, they take water on to be able to dive down, and they dive kind of like a dolphin, and then they let the water out to come up to the surface. When they're underwater, they are unable to communicate until they get back up to the surface and they can connect to the satellite to communicate back. And what they're doing is, in this particular context, we were looking for what's called an ocean front. So an ocean front is very similar to a weather front. In general terms, you have cold water coming up and warm water on the surface that's going down. And so you're looking for these changes in the water in order to identify what's going on. And that can be based on geological features. It can also just be based on other aspects of the ocean. We also deployed these 2 ocean surface vehicles that were developed by the College of Oceanography. And then on top of that, we had an ocean drifter, and then we had the ship itself. So this was a 3-week cruise. We conducted something like 10 missions. And a subset of the missions were fully autonomous, meaning that the gliders and the surface vehicles, their paths were planned. They were set into the ocean and set off to explore a region. If they found an upwelling, they were supposed to request new plans that would allow them to sample various scientific information about the upwelling and do that repeatedly, kind of in a zigzag pattern across the front. They also had to be able to avoid each other, but they don't have sensors to sense each other. And since this is in the Gulf of Mexico, there's a lot of stuff in the water. You've got, of course, all of the oil rigs. There's a lot of commercial shipping and then a lot of personal watercraft as well. So this is a pretty complex area to work in. And in this case, the oceanographers were the ones who were our primary user, although the roboticists were really there doing a lot of the work. But if we were to think about how an oceanographer would use this system, again, you can see that this is very different from what you saw a few minutes ago. And the oceanographer really wants this to be an autonomous system. And in many ways, it has to be, in that today, when oceanographers deploy to do this mission, they often are unable to identify an upwelling in situ, meaning that they take all the information that they collect from these vehicles and they bring it back to shore and analyze it post-deployment to identify where they potentially saw upwellings. Now, the difficulty here is that you speak to 3 different oceanographers, they will give you 3 different sets of criteria that they use to identify those upwellings. And so you try to encode that into a decision support system that allows them to identify that upwelling while they're at sea. So this ship here cost about $30,000 a day to lease. And we did a 2-week, I think it was a 2-week deployment. So it's very expensive to be able to do these real deployments in the ocean. And so you want to be able to identify exactly when that upwelling has been detected so that you can ensure that you're actually getting the scientific information you want to collect about that feature, if you will, in real time. And so if you think about that in this context, there's this idea of how do we use history-based information? And here it's more of how do we use bathymetry information? How do we use information collected on prior deployments to help identify areas where there may be more likelihood of these upwellings occurring? And then how do we get predictability about the performance of the vehicles? So when the gliders go underwater, we always assume generally that they're not going to come up where we would expect them to, because you've got ocean currents, there's going to be drift in the internal measurement unit, the IMU of the vehicle. So it's not going to come up exactly as the path was planned. With the surface vehicles, you do have a little bit more reliability with what they can do. However, you still have some drift with the vehicles due to the currents as well. So how do you get predictability that you're getting accurate information that the vehicles are covering the areas you want them to cover when they only can give you small bits of information back? Because you don't generally have cellular coverage out in the middle of the ocean. So you're relying on satellite communication, which is narrow bandwidth, very expensive. So you're only sending really important pieces of information back about what's happening with the system. And so that's where the decision support comes into play, so that you can try to predict what's going to happen when you're making those plans about where the vehicles are going to go, how they're going to drift, et cetera, to ensure you're covering as much area as possible, as quickly as possible, given the cost of the deployment, for example. So you also need adaptability. So how do you communicate how the systems are adapting if they're going to in the real world environment to the human, and do they even need to do that communication? So if the vehicle is adapting to get back towards the point that was originally planned, the human probably doesn't need to know that unless there's a problem, right? So that is, you could argue, an aspect of transparency and explainability, but the human doesn't need to know everything, right? If you're going to communicate to a colleague to come to your home, you give them the address and you might tell them some landmarks to allow them to figure out how to get to you, but you're not going to give them, step-by-step, meter-by-meter instructions, and we don't want to be doing the same thing here. So it's this trade-off of too much information versus enough information to understand what's going on. So I'm also going to go to the next, go back to the DARPA offset that I was talking about before. So remember, I said before, we have really limited communications. These vehicles are very inexpensive. So DARPA is not giving us money to buy vehicles. They're giving us money to bring the system into fruition. So on average, we spend about $5,000 per vehicle, which is not a lot. We're not talking about advanced processors here. We do have JetSim processors on the ground robots and on the UVIFI EFOs, these vehicles here. But as I said before, these vehicles only have Raspberry Pis and a PiCam, which is $20. You can see that there's a RealSense camera on here. We do have GPS on all these vehicles. We also have RealSense. This is an older picture of the ground vehicle, but we have RealSense on here. We have $100 laser rangefinder, which means that the sensors are less accurate and less reliable than, say, the Velodyne laser rangefinder you would find on an autonomous car. It doesn't have as much accuracy, for example. And we're in, environments built for humans. So there's stairs, there's buildings, there's curbs, etc., that we have to deal with. So, and we have one person. We call this person the rear tactician or the rear operator. And for this particular deployment, which occurred about 18 months ago at Camp Shelby in Mississippi, the area of play was basically this area where my mouse is covering. So you can see these flagpoles here that represent robots in the takeoff and landing zones. And the operator was stationed in this building right here. So the operator is wearing a virtual reality headset. They cannot see anything that's happening outdoors. And so they're getting all their information through this interface. And what you're seeing here is kind of a top-down view of the virtual reality environment. The flagpoles are used to communicate what the state of the vehicle is. Is it in communication? Is it returning to launch? That's particularly important for the aerial vehicles. Is it actively tasked? Those kinds of things. So high level information for the operator. And we are covering this entire area. The robots, if they leave from where my mouse is and follow this road down and around kind of the lower village and come back up here by the mosque, and then come down this street here, which this is a police station right here, and back around, that's about a half a mile. So it's a pretty long area for these ground robots to go around. So this tactician, if in this particular deployment, we had about 65 robots that we were deploying. So that's a lot from a human factors perspective. The human cannot be paying attention to every single vehicle. They are not able to task every single vehicle. They have to do it in subgroups or as a swarm, meaning all of them together, for example. And so you can see here that for the rear tactician, there's a lot more to this concept of transparency. So history is probably less so than the reliance, right? So how reliable is the information that you're getting? And that's part of, how long has the vehicle been out of communication? If the vehicle's out of communication, it's not updating on the monitor. So you really don't know where that vehicle is. But what we do know is if that vehicle has been tasked, that vehicle is going to continue to do its task autonomously, whether it's communicating with us or not. Now, the downside is that it could finish its task and still be out of communication, which means the vehicle is just going to sit there for the rest of the mission and not be useful. What we're implementing for our next deployment is that if a vehicle completes its task and it's out of communication range, it's going to go back to the last known location of communication so that it can update the system and make that robot then available to be tasked through the mission planner, for example. There's a lot of aspects of human factors in this rear tactician for gaining transparency. You have to understand what their workload is of the human. how many vehicles are they monitoring overall? So how many subtasks are going on? One of the things that we often do is we'll deploy teams of 5 vehicles, 4 forward-facing camera UAVs and 1 downward-facing UAV to surveil the sides of these buildings and the top of the building to collect information. And so we'll have 10 of these groups going simultaneously as they try to investigate a set of buildings up here or a set of buildings down here. I say 5, that's with our most recent deployment where we had more vehicles. We had 60, we were probably doing about 3 of these at a time because we also had ground vehicles gathering information, for example. So, you know, there's aspects here that have to be addressed with that. How do they observe what's going on? So if I go back to this, we've done this mission a number of times, and there was an April tag right here that represented a bomb. And so there was one time where the GPS error on these 3 ground robots up here that were tasked as a team to kind of go down this road and collect information, where one of them saw the information, but it showed up all the way over here in the forest because of the fact that there was GPS error. And so, you know, you're looking at that, and because we had seen it multiple times, we knew where it should be. But if we didn't know that, how do we get that corrected? How do we know that where that thing actually is? And obviously we know it's not in the forest when it appears, but how do we know where it actually is? You know, so you want the vehicles to be able to adapt in that case and gather that information and get more, if you will, sensors on that piece of information so that you can get a better representation of where it's actually located. Even if there's still an error that's a few meters, you have a much better idea of where it is and how you can respond to that. So these are all aspects of things that we need to consider. And, you know, like I said at the beginning of this talk, there's been a lot of conversation over the last year, 2 years about explainability and trust. You know, how do we trust autonomous vehicles? How do we trust, you know, UAVs that are potentially delivering packages for us? And really the point that I want to make here is that it's really much more than that. You have to have robot decision-making that can be understood by the human users, whatever that context is and whoever that user is. And that it's very different for different applications, different domains, and different users within a particular domain. So the point here is that explainability and trust are really insufficient on their own. You need more to the overall system in order to be able to do that. So it's a much broader concept that we have to deal with, and really goes to this human-machine teaming aspects that I tend to work on. So with that, I will wrap up, and I thank all of my research sponsors, and of course, the plethora of students who've worked with me either currently or in the past.
Yeah, thanks a lot, Julie. So I'll open up for questions. I'll let you think for a second if you don't already have a question, and I'll just start with my own. So I'm, well, I guess you can't see them out your window, but at OSU, we have all these delivery robots running around the campus, as you've seen, I'm sure, and probably a lot of others have seen if they visited campus. They're pretty interesting that, you know, so real world live demonstration and application. And I thought it would be interesting to get your perspective, maybe critique on the transparency issues that they're getting right or wrong, perhaps from different perspectives.
Sure. I have not. So this is a picture of the robots that Alan's referring to. So I have not actually physically interacted with one of these robots. I have seen them from afar. You notice that they have flags on them so they can be seen. This is particularly important if you're driving a vehicle through campus. And as you know, if you know, assuming all of you are either alumni or current students, you've been to campus, so you know what beautiful foliage and bushes and such that we have, but that can also hinder being able to see these robots as they're driving around. So the flag is really important for making it clear what's happening. Now, one of the issues that was a problem early on when they deployed these, and I actually haven't been able to follow up and see if they fixed this issue, but what was happening is the robots would come to an intersection and people driving wouldn't know what to do, if they should wait for the robot to cross the street or if they should just go through the intersection. And apparently there were a lot of these kind of standoffs where the person didn't know what to do, the robot just kind of sat there. And so that is a case where transparency is really lacking. That unknowing user of the, unknowing driver, for example, a user of the technology didn't know how to interpret. And if you're following the rules of the road for Oregon, for a human in the crosswalk, you have to stop, right? So do you apply those rules to this robot or not? That's an unanswered question at this point. It's not something that the state driving rules cover. You're not going to be tested for that when you take your driver's test. So there are different aspects here. I think it's a little bit better for those who are actually receiving the food, but I haven't actually talked to anybody in that regard.
Yeah, thanks. I've been in one of those standoffs, and I've just learned to go after a while. It seems like they will stand off as long as you stand off, as far as I can tell.
And you just went, Alan?
Well, I waited for a while, of course, and then it's like the red light that never will change. You have to yes. Eventually you got to go. But yeah. So do we have any other questions from the audience? We have a few more minutes here.
There's a video of these if anybody hasn't seen them.
Yeah, they're pretty cool.
Alan, I have a question if no one else does.
Yeah, go ahead.
Let me mute that. Go ahead. I'm going to play that while skip the ad. Go ahead and ask your question. I'll play the video while we're talking.
Yeah, so I'm curious. You have that map to think about the criteria of transparency. Have you built a framework around that to actually quantify that or measure it? At the end of the day, for example, when you're doing something like fielding, let's say a piece of military hardware, you have to decide.
Sorry.
Should I field it?
Hang on one second. Sorry, there's a huge bug in my office. Like, it just went behind me. Okay, it was huge. It was like this long. I don't know what it was. So you asked if the concept map, if we've applied it to things. Yes, we have actually. We specifically developed that for swarms or collectives. And what I mean by that is very large numbers of robots, very complex systems. And we did some work for Office of Naval Research in which we conducted user evaluations for colonies of agents. So we had 4 colonies of 200 agents doing a search task of an environment and trying to identify the highest value site within that environment. So it's based on the honeybee algorithm for selecting a new nest when a subset of the hive leaves to establish a new colony, new daughter colony. And so one of the issues you have for transparency, as opposed to some of these individual human factors like usability, workload, situation awareness, is that how do you assess it? How do you measure it, right? And so my former student, Karina, that was one of the things that she was working on, is how do we assess transparency? And so you do end up using some of the standard human factors metrics, like objective workload metrics, objective situation awareness metrics, or trust metrics, things of that nature. But you also have to put it into this broader context and look at how the metrics are related differently than is traditionally done in human-robot interaction or in human factors. People tend to look at those factors independently, or maybe only situation awareness versus workload, but they don't look at it in this broader transparency concept. Does that answer your question?
Yeah, thank you.
Yeah, Art, you had a question. Do you want to ask it yourself?
Sure. Where does human machine interaction appear in transparency most importantly?
I don't know that there's one place where it's most important. I would argue with any system that you interact with, establishing that interaction is important. Now, maybe let me rephrase a little bit what you ask. So if we're talking about the human interaction with a cell phone or a computer, which is more traditionally called human-computer interaction, then there's probably less need for transparency there. It needs to be easy to use, but if I mess up my phone or Microsoft dies on me, it's not going to cause any great damage to me. It's not going to cost, OSU hundreds of thousands of dollars, right? Now, the term that used to exist was called complex human machine systems. And what that typically referred to is something like a power plant, control room, or pilots in an aircraft, for example, especially as autonomy has increased in aircraft. And so you have these very expensive systems where if something goes wrong, then there are very large implications. And robots kind of fit in between the two. They are not human-computer interaction because, this robot that you're seeing here on the screen is quite large. And if it runs into you, it's going to hurt you. If it runs into your car, depending on where it hits your car, it's going to do damage to your car. Now, that's not hundreds of thousands of dollars. Well, without the lawsuit, it's not hundreds of thousands of dollars. But there are some significant implications of it not doing the right thing. And then when you talk about the systems that I use, or you talk about integrating UAS into national airspace for something like delivery drones, well, then you do have some higher consequences. So this concept of transparency, I think, becomes more important when you have robots involved in real world scenarios that we want to be able to place robots in the future, especially, I work a lot in disaster response and military domains. So there, the humans are more looking at the vehicles to be tools, if you will, rather than friends. And so the robot has a very specific task to do. The human cannot be paying attention to what the robot is doing. If you're talking about a fire team trying to dig a fire line for a forest fire, if that robot is supposed to be digging a fire line and the human is off in another area digging part of that fire line, can't be telling that robot what to do all the time. And so that's where teaming becomes really important. It needs to act as good or better than the person in some regards, but not be a humanoid and not have human traits necessarily.
Thank you.
You're welcome.
Yeah. Well, I think I will, unless somebody raises their hand, I'll just take the last question. And yeah, so I was just curious kind of to get your predictions and thoughts on sort of the timeline of the following three things. So, when in the future do you think we will start seeing UAV drone delivery, right, to our front yards? When do you think we'll see the ground robot delivery, of the type that you were talking about with Digit to the front door? And when do you think we'll see a robot plumber emerge as an effective entity?
Okay, I'm going to go a little bit out of order there because I'm going to put them in the order that I think they will occur.
Okay.
And by the way, my disclaimer is none of what I say is the perspective of my sponsors, including the FAA. So, so I think Digit, from what I've seen, and I've only seen basically what everybody else has seen. I think the likelihood of Digit being able to deliver packages is near term, what I would call 18 to 24 months, maybe. Jonathan may disagree with me, but from what I've seen, Digit looks pretty capable of doing it. Now, there's other things that have to occur for that or other parts of the system that may have to be developed to support that, right? So how do you outfit a truck to accommodate a digit and those kinds of things that are beyond the capabilities of the robot? They're more of the system of systems aspects. Delivery drones. That's going to be a while because the FAA is very cautious, as they should be. I can tell you that there are definitely companies out there that are ready to do so and are doing so in other countries. And so there are places like Australia, some places in Africa, where there are things being delivered, and they are testing in certain places around the United States for delivery drones, but they're very restrictive. To see them on the scale of the Amazon trucks that drive around, I think that's going to be a ways off. The vehicle should be capable of doing it, I would say in 5 years. But whether or not the infrastructure exists to provide the safety that's necessary for the FAA to approve it will be another question. And then the plumber requires, I think, a much higher level of intelligence than those other two systems. So there's the level of intelligence, there's the level of dexterity, there's the level of skill that the plumber has to have that is going to be very hard to get into a robot in the near term. And we're probably looking more like 20 years, 25 plus years for that, in my mind. I could be wrong. Deep learning has solved a number of problems. The advent of the iPhone just made a decade worth of capabilities available for robots that we hadn't seen change in 20 years. So there is the likelihood that something like that could happen to help us build that robot plumber, but I still think that's pretty far off.
Yeah, thanks. That's an even optimistic estimate from my point of view for the plumber, but yeah, I'd almost say never, but little plumbing assistance maybe. But
well, it might be cheaper than hiring a rear plumber lately, so.
True. All right, well, thanks a lot, Julie. That was a great talk and interesting discussion. So yeah, everybody stay tuned for, we'll announce what's going to happen next fall, sometime later in the summer. And yeah, everybody will just thank Julie again, and we'll see you next fall.
Great. Thank you.